Hey everyone, and welcome to this video, and I would say welcome to this full stack machine learning mastery course. So in this video we'll be continuing our theories. First we have all talked about linear, we have mastered it with some regularization techniques, and then we have talked about logistic regression, and then we have done some cool projects. Now it's time to get into another great algorithm, which is support vector machine. In this video, I've seen on YouTube, there are many instructors who teach support vector machine, but they don't teach mathematics to ace any kind of interview you face or any kind of problem you face. And many beginners have a good amount of set of problems. What are they talking about? So I was also a beginner, so I understand what actually the need of yours, because I'm a student and I know from my perspective how I think that should be explained. So that's a reason easily explained. So in this video, I'm going to talk about everything you need to know about support vector machine to ace an interview about support vector machine, and in depth with mathematics. So here is an outline that we'll be discussing about. You can see over here, I will come to this later on, but I would like to, before going into this, it takes a lot of time to do all of these, so be sure to subscribe to this YouTube channel, press the notification bell so it always motivates me. Okay, so in this video, I'm going to start with introduction to SVM, and then I will a little bit go further to talk about linear support vector machine. Then I will talk about hard margin classification, then soft margin classification. Then we'll talk about kernel trick. Then we'll talk about actually the math behind support vector machine with two kind of problem, with primal, dual, and then we move on with modern methods of optimization, which is subgradient and coordinate descent. Okay, and then in 7th we'll talk about empirical risk minimization, and these things, primal, dual, subgradient, and coordinate and empirical risk minimization, is not being taught on YouTube. The reason why, I don't know about that, but we should get into maths also. What are the kernel tricks which are available, and also the math behind that to understand how actually the algorithm works. Because many instructors say that you don't need the maths of SVM, but you need maths for every algorithm. So that's why I've come up with this video on the support vector machine. Maybe the next video will be on principal common analysis. Again, with two good tutorial onto principal common analysis. You don't need any kind of mathematics even for this video, but you need basically for our basic algebra. Okay, so let's start off with introduction to support vector machine. So you can see over here that I have a small pic in front of me, and this pic is simply a support vector machine pic. But before that, I want to just give you an introduction of what do you mean by support vector machine. So support vector machine are one of the best algorithm, one of the most powerful algorithm. You can read who has introduced on a research paper, but one of the powerful algorithm for classification and for non-linear classification and for regression task also. So we will go theory into the end in this video, but what actually the SVM do? SVM simply what it does, it makes in hyperplane. This is the red one is called the hyperplane, and this is called the hyperplane, which separates out the example. So let's say that you are building a face recognition system. Okay, so you are building a face. Although this will be a long video, so I have written the outline, so I will sing here what to next. Okay, so let's say you're building a face recognition system which just recognizes let's say two person, which is I wanted to name as maybe the Ayush, and maybe the another person, let's say Krish. Okay, so you have a two person, and you need to classify this person using the face recognition system. For an example, so you have written Ayush as a label 1 and Krish as a label -1. So you can see over here that these are two examples, and then what we done, this is a linear data, so we have made one hyperplane, and these examples are Ayush means my face, and these are the Krish face. Okay, so this is 1 and -1. So you have separated out, so whatever the new example will come will fall into this hyperplane, and it will be simply classified as the Ayush, and if here it's simply classified as a Krish. We'll talk about how this happens, what prediction will happen, how it makes prediction, etc. later on. What was the actual intuition you have to take from this slide is it's construct a hyperplane. It's construct a hyperplane which separates out of two examples, two classes. Okay, in case of linear classification. Okay. Pretty much easy. What I'm trying to say you here. Okay, so now I'm going to talk about what actual the linear SVM does. So I'm going to explain you a little bit more about a linear support vector machine. Okay, so what happens actually? Yeah. So we have talked about the support vector machine is simply construct a hyperplane which separates the two examples, well, one for a 1 and one for -1. In case of that, Ayush was encoded as 1 and Krish was encoded as -1. Okay, so this is the basic encoding that we have done in our previous slide. So linear SVM is bit the same. So let's again take the example of face recognition system. Okay, so I'm going to take this as an example of this as an example that you want to build a face recognition system that will give it a picture X. It will classify the label as Ayush and Krish. Okay, so let me write. You have a training data set. You have a training data set, I would say training data set, and there you have one training example and the corresponding labels. Okay, and you have again some more training example, then you have a same label, corresponding label, all the way down to the number of a training example xn and yn. Okay, so you are trained here. It might be my picture and it label as a 1, my picture, and it might be here the Krish picture and label as a -1. But don't think that is a negative. It's a -1 encoded. We have encoded. We'll talk about why this is the kind of thing later on, but you can see about that we have a training data set like this. Okay, so what we done, this is our, let's say, x where y1 equals to 1 and here y1 equals to -1, and again 1 is Ayush and -1 is Krish. Okay, so we have made one up. This is a linear. Our data is linear over here. Okay, however, in real life it's a bit rare that you see it all. But you have made a straight line. But you have made a hyperplane with two parallel hyperplane that separates it out. That separates the nearest training example. That makes a maximum margin. But it may happen that you are not able to understand what I'm saying this now. Leave my 2 to 3 lines before. Just don't worry. I will come to that in hard margin. But here in support vector machine, what you are doing, you are just constructing a hyperplane, just for sake of an example, and you have a training data set like this, which is the x1, y1, x2, or y2, and all the way down to the xn, yn, and you have a data which is y1 here and a y1 -1 over here. Okay, so if we separate it out, and whatever the example will fall, you can say that okay, that's the Ayush and that's the Krish. Okay, so the question may arise, hey Ayush, in linear regression, we are simply making a straight line. We are simply making a straight line, and we are not doing the classification over there. We are not doing a classification over there. But in the linear regression, we are just doing the straight line. So in linear regression, we are just this is called the hypothesis in linear regression. So we're just making this theta 0, or I can say theta transpose x, which are computing this straight line or the hypothesis. Okay, so what happens in case of support vector machine? What happens in case of support vector machine? So we compute this hyperplane. The hyperplane can be written as W transpose for this hyperplane. It should satisfy this condition, which is W transpose x minus B equals to 0. This is the hyperplane. From this we can construct our hyperplane. So let me make it more formatable. So in this way we compute our favorite hyperplane, and which should satisfy this W transpose x minus B equals to 0. And you may think, hey Ayush, what is W and what is B? W are the feature weights. W are the feature weights that we have already talked about. What is feature weights? They are that we have to learn. Means in case of linear logistic, we have a theta. So we have in a W, and B is the bias term. The B is the bias term or the intercept. Okay. So we have a simple hyperplane, and we have computed a hyperplane as like this, and it should satisfy this hyperplane condition. And we can write this as like this: W transpose X minus B, which is equals to 0, and that's what this hyperplane has been computed. We will get to this times and times to get you a more intuitive example of this hyperplane. Okay, so in summary of this slide, what we have done so far, we have taken an example which is fixed recognition system, which will classify two names, which is Ayush and Krish, based on its faces. So we have a training data set x1, y1 x1 and corresponding labels y1. Okay, and we constructed a hyperplane which is written by this, which satisfy this condition, which is W transpose X minus B, which is equals to 0. Okay, and whatever the value will come will be this in this range. It will classify this as Ayush, and it will classify this here as Krish. So let's say come here, then we can compute that as oops. So sorry, I don't know why. Okay, great. So let me make you one thing familiar with. Okay, so I have written it once again. So what you do in summary, we have this system, and we are just making this. What you have to take away from this slide is W transpose X minus B is the formula for computing this. Should satisfy this condition for computing this hyperplane. Okay, so we are talking about linear SVM over here. So we have talked about linear SVM over here. So let me write it down over here. Linear SVM. Okay. So now let's talk about hard margin. So again, we will revisit how it is computed, etc. So what we were doing is in linear classification, we are just creating a hyperplane over there given some training data set. So we are creating it's the same that we were creating before. So this hyperplane is this is W times X minus B. This is W times X minus B equals to 0. Whatever on or below, on or above this line, hyperplane is regarded as a 1, which is in case Ayush. Okay, and whatever below below this hyperplane is regarded as a Krish. Okay, so recall that we were building face recognition. Oops, I want some eraser. Yeah. So we were building we were building face recognition system that classify Ayush and Krish, and we have encoded Ayush as a 1 and Krish as a -1. Okay, so what I'm telling over here that you have constructed a hyperplane because it's a linear data. So I've constructed a hyperplane with a condition which is W times X minus B, which is equals to 0. You can write W transpose X minus B. It's just the same, but in this case it's a vector. Okay, this is a vector. So you have computed that hyperplane. This hyperplane. Now it's time for making predictions. So how you make prediction in classification? So here you set a condition, whatever W transpose WI XI, I think so, W transpose XI, oops, minus B is greater than or equals to 1. Okay, for all I, means again I'm saying that you have WI transpose XI, W transpose XI minus B, whatever the output on or B or on above this hyperplane is regarded as a 1. What I'm again saying, whatever output will be on here or above here is regarded as a 1. Okay, will be positive, which is Ayush. Okay, and whatever below this hyperplane, this below is regarded as a -1, which is in case crash. Okay, so what I've said till now, that we have constructed one hyperplane which is W transpose X minus B, and we are making predictions. How? We are making prediction by simply whatever on or above the hyperplane is regarded as a 1, which is our output, which is Ayush in this case, and whatever below this is regarded as a -1, which is crash. Okay, so it's a bit easy. I think so. It's a bit easy. So you may think, hey Ayush, how we are separating this? So we are constructing two parallel hyperplanes that separates out, or that maximize the distance from the nearest data point. Again, you may think, hey, you're confusing me like other instructors. No, just wait at what I'm saying. Just wait at what I'm saying over here. So these two are parallel in support of a machine. These two parallel lines are created. These two parallel lines are constructed. Okay, this is also called the parallel hyperplane. So this is constructed, and we always want to this is called these are the margin. These are the margin. Is we want to maximize to get better prediction. Okay, so to maximize and it's in such a way that the nearest data point from this has a maximum distance. This is the nearest data, so it has a maximum distance to the hyperplane, which is W transpose X minus B. So it has a maximum distance from the nearest data point. Okay, so that was the two parallel lines is doing. So for maximizing this margin, this is called the margin. So for maximizing this margin, this margin is calculated by 2 over the norm of W. Okay, and W is the feature weights, so 2 over the norm of W, and these how it is calculated. So for maximizing this margin, we want to minimize this W. Okay, so for maximizing, so if you have a minimized W, then you will see that our distance is large. Again, if you haven't understood, don't worry. It's very, very easy. Again, I'm repeating once again to get you a better feel. So what we have done so far? We have started with face recognition system, which simply builds whether the particular image, given an image, a particular image is a Ayush or a crash, and Ayush label as a 1 and a crash label as a -1. Okay, so we have constructed one hyperplane, and hyperplane is labeled as a constructed by W transpose X minus B equals to 0, which is satisfy that condition. Okay, and anything above means above this hyperplane or on this hyperplane is labeled as a 1, which you can see over here that we have given one here, and whatever below this hyperplane is known as whatever below this is known as the -1 onto this. Okay, so this is regarded as a -1 that you are seeing over here. This is regarded as a +1. Okay, so let me write, and then we construct two parallel hyperplanes. That is means we construct two parallel hyperplanes that have the larger, that in such a way that the nearest data point. So we let me write so that we make two parallel, I will write parallel hyperplanes that have the largest distance, that have in such a way that the nearest data point has the largest distance from the hyperplane, from the main hyperplane. I will write main hyperplane, that red one. Okay, so this is what actually it is doing all. So we have constructed, and here you can see that this one has the largest distance, and these are called the support vectors, by which these are called the support vector. This blue and this green here are called the support vector, which is supporting I'll say the parallel hyperplanes. Okay, I think that's we have got it till now. Okay, and this is called the hard margin classification. The reason I'm calling, we strictly impose that our data point should be outside that. Should be outside means should be largest distance. Should be not should not be into this. So it should not be into this. It should be always on or means here, either on or above this hyperplane, parallel hyperplane, or on or below this hyperplane, and these are called the support vectors. So that's why it's named as a support vector machine. Okay, so this is a very easy to understand, and this is called the hard margin. We are strictly imposing to be get out, means not come over here to come nigh range. So that prevents that is prone to overfitting. Maybe if you means it's prone to overfitting. So that's why we can make some release that we can so we have introduced a soft margin classification. Maybe you know, but what is, hey Ayush, what is soft margin? What is soft margin classification? So till now we are dealing with classification. Okay, so what is soft margin classification is, but before that I left one thing. Is the one thing that I left is we can write our optimization objective. We can write our optimization objective as like this. So we can write our optimization objective as we want to minimize the norm of W to maximize that. I'm going to minimize subject to W transpose X minus B greater than or equals to 1. Okay, so this is our optimization problem, and we want to minimize. Obviously we want to minimize to get a good predictions, okay, for the training set, but I don't know what will happen in a testing set. Okay, so we have now we'll talk about soft margin classification, so that you can get a better feel about what is soft margin classification, etc. In soft margin classification, what we do, we introduce one hinge loss. What this hinge loss does, we give some release. Okay, you can do this. You can do this. You can have some data, means have some points not too larger. We don't want to maximize always. So when we give some release, okay, you can we don't have a strict thing. We have a little bit not a strict thing. Okay, so it is less prone, it's more robust, it's less prone to overfitting, and will generalize well onto the testing set. So we have a hinge loss, which is hinge loss means a loss cost function. Again, the hyperplane formula is same. So we have introduced one hinge loss, which is given as 1 over n plus for all data points I equals to 1 all the way down to the m, just saying max of 0, 1 minus yi W transpose xi minus minus b. Anybody, if someone was there, can be pointed it out. Oops. Okay, so b and plus lambda the norm of W square. Okay, hey Ayush, what you have written over here? This is called the hinge loss. Obviously, I have sent you that this is called the hinge loss. Okay, so this is a cost function. So what we are doing over here, this is the j of W comma b. Okay, so this is a hinge loss 1 over n is the number for training examples, plus all the way down to the n, and this we are doing this for good derivatives, which we'll talk about later on. So this we are taking the max, and yi is the ground truth, and W transpose xi is the model predicted value, which is I can write y hat, and we are adding lambda and the norm of W square. Hey Ayush, what is lambda over here? So in the previous in hard margin, we are strictly imposing to maximize this hyperplane to this parallel margins, but here we can control that using a lambda. So you can see over that we have constructed, and this is our kind of thing like this. Okay, so sometimes you will see that it is denoted by C. Okay, so let's denote for now as lambda. Okay, so in lambda, what we are doing, we can control this width, this margin using the lambda. Little bit tricky over here. If you increase lambda, let's say lambda equals to 100, it will be more close. It will be less close, means it will be like this. Let me make you what I'm saying over here. Okay, it will be like this. So it will be less width. It will be less width. Okay, if we decrease lambda, if we increase lambda, the width will be large. Okay, so if you increase, now it will be, and it's strictly imposed. Okay, like this. I think so. Okay, this is how all it works, and I think that you can control the width by the lambda. Okay, you can control the width by the lambda, and it simply means that if lambda equals to 100, we will usually take lambda equals to 100. And you can see over here in internet about some pics about what is the lambda and support vector machine. Okay, so you have this, and it's very easy. This is the hinge loss, and we are just this lambda again is we can control the width of that margin. Okay, pretty much easy. Now it's time for getting into the non-linear classification. So we have talked about soft margin, then we have talked about the hard margin, then we have talked about linear SVM. So now it's time for getting into the non-linear classification. So it obviously happens that you have a non-linear data rather than linear data. So there are some other trick, which is kernel trick, which is known as kernel trick, which we can SVM is more SVM powerful on non-linear classification because of kernel trick. So it transforms your data. What it does is takes your data and transform the data to the I will talk about what is the equation, etc. So it transforms your data like this. So you apply some transformation and it will be like this. So the non-linear becomes the linear. Okay, so I will tell you what we are doing over here. But let's talk about in non-linear what we are doing. So we have 4 types of, there are a lot more, but I will talk about I think 4 types of, I will talk about 3 types. Sorry, I will talk about 3 types of kernel tricks that we will focus on today. So what is you will get to know from this equation what actually the inner working of this, what actually it is doing. So the first thing we're going to talk about is polynomial kernel trick. Polynomial kernel trick, which is homogeneous. Okay, so this is called a polynomial kernel, which is a homogeneous. So how we define? We define by the similarity. I will leave k as a similarity xi for the point xi comma xj, which is a vector, equals to the dot product of xi, the vector, and xj dimensions. Okay, so it's defined by like this. So you have just one vector xi and xj, which is a data point. Okay, which is a data point because we are transforming our data point. You will, if you're not understanding, don't worry. I was also not understanding it at first, but after you move on, you will see how it is working, etc. Okay, so after some equation you will get to know how it is working. So you're just taking the dot product, but you may think, here Ayush, what is xi and xj? Is a data point that we need to transform. Okay, you will get to know what I'm saying over here. But actually, what is homogeneous? There are polynomial kernel trick which is homogeneous, and which is polynomial kernel trick which is inhomogeneous. So in polynomial kernel trick homogeneous means if you have a same degree of polynomials, all the terms have the same degree. For example, so I've written one example, x5 plus 2x 3y2 plus 9xy squared. Okay, so here the degree of polynomial is 5, which is all the same. You can see over that it also have a 5, it also have a 5. Okay, I think it's a 4. Okay, so you have all the 5. The degree here is 5. Okay, so I will remove this. You can search more on the internet about a homogeneous. Okay, so you have like this is just use just xi and xj are the vector, which is a data point, and then there's second type of called a polynomial kernel, which is the inhomogeneous. Okay, the equation can be defined by, again you take the same thing xi xj, and you transform this into the taking the dot product of xi times xj plus 1. So you add 1 to them, d. Okay, pretty much easy. There are two things that we have talked. So it just transform your data to be I will talk about to perform non-linear classification. Okay, so we have talked about polynomial kernel and homogeneous. But one more kernel that is that all of them use, which is called the RBF kernel or Gaussian kernel, but we'll denote RBF kernel, which is a radial basis function. What do you mean by radial basis function? This is and this is called the RBF kernel, and it's defined by something like this. So we have a exp exponent of minus lambda. I have to see the equations. Minus lambda, taking out the norm of the distance between xi minus xj, okay, the distance between squared, okay, and lambda is greater than 0 for lambda is greater than 0, and lambda is sometimes parameterized by 1 over, I think, minus 2. Okay, so 2 times this, I think, so you can write this 2 times the sigma square. Okay, you just remove this. Okay, so you have a 2 times sigma square. So lambda is parameterized by like that. So what we are actually doing is we are taking out the distance between xi, one data point, and another data point. Let's say here, yeah, let me draw it like this. So you have a xi and you have a xj, and taking the distance and then you are multiplying with taking the norm of that, means the norm of a vector, and then you are adding one more data, and you are removing these two data points, which is called the landmark or the similarity, and you just transform your data to be another data point. Okay, so we'll talk about more about this later on. So how actually the model predicts using this non-linear. So what we do, we take out a vector, which is w. We take out a vector w, and we simply multiply with the kernel or similarity. I think similarity of it's a x. Okay, similarity of x. The similarity of x is this equation. You're just doing that, and that eventually equals to I equals to 1 all the way down to the n, all the way down to the m. The similarity of x. Okay. Similarity of x yi kernel of xi minus xj. I think so. Okay, so here is the optimization problem we have got. So you are just multiplying yi, which is ground truth, and here is our model predicted value. Okay, so you're just multiplying it out. You're just multiplying with the similarity of that x. Okay, and it may happen here usually you're telling this is not digested from your belly. So don't worry, it's again what you are actually doing kernel trick, transform a data to perform a nonlinear classification by actually making the data linear. Okay, so just applying a nonlinear transformation over there. Okay, you just make this any kind of a data point to be this another data point. Okay, so just making a to a square like that, and in another example. Okay, so you can see over here internet about the actual equation. I don't know, I've written correct over here, but it's obvious. You're just making prediction with the transform vector times the weights. Okay, weights times the transformed vector x. Okay, so now we have talked about a non-linear classification, how we do that. Okay, so now let's talk about the math behind how actually we minimize our loss and etc. So there is some kind of thing for writing or computing the SVM soft margin classifier, because if you have a strict lambda, then obviously it will become hard margin that you are not imposing anyone to come in between. But if you're having a good if you have a good lambda, then you are allowing some thing. I hope that you have already seen that soft margin slide. Okay, so I'm going to spend on a primal problem and a dual problem, and then I have a Subgradient and coordinates a descent. Okay, so we'll do it a little bit more faster, but if you're not able to understand the dual problem, don't worry. Okay, so you have in primal problem, I will write it in a very smooth way so that you can see all as a notes. So in primal problem, you take for each I to be the member, I will write for each I to be the member of 1 all the way down to the n. You introduce a new variable which is known as zeta. I don't know how to write zeta, so this is the zeta over here. I will write this as a zeta. Okay, so this is zeta. Obviously it looks like epsilon, but don't worry, it's a zeta equals to the max of 0, 1 minus yi w transpose x minus b. And you may think, hey, you should just look the same that we have seen in hinge loss. Yeah, it's the same. So you introduce a new variable, which is zeta, and you make him contain this max of like that. Okay. Okay, so where zeta is the smallest positive integer who is greater than 0, the smallest positive integer. So for yi, I will write this as for yi W transpose x minus b. For zeta is greater than or equals to 0, which is a non-negative. Okay, which is a positive, non-negative positive number. Okay, I would say means a positive number, smallest positive number. Okay, and you wanted to minimize, so we can write minimize 1 over n. I'm writing minimize over here, 1 over n, I equals to 1 all the way down to the n. Then zeta, which is defined like this, which is defined like this. You can say a max of etc. Okay, zeta plus lambda of norm of w square, and lambda determines the offset, means the margin. Okay, with subject to oops, I don't want to delete it. Yeah, subject to yi w transpose xi minus b for all 1 minus the zeta I think I and zeta should be the greater than, and zeta for zeta I should be greater than or equals 0 for all I, which is all I. Okay, so we are just doing the same, but we have introduced one new variable, which is zeta I, and we're minusing from there. Okay, so just minimize this cost function. Okay, so this is the means kind of a past historical methods, which is called the Primal problem. I will introduce two modern methods which works best: subgradient and coordinate system. But if this is just the same, you introduce a new variable, it's just like a hinge loss that you want to minimize that hinge loss. Okay, and if you don't know about cost function, don't know about gradient descent, do watch my video on linear logistic, then it will be more clear. Okay, I don't want to get into cost function and gradient descent. Okay, so now we have seen the primal problem. Now let's see dual problem. In primal problem, we just want to minimize our cost function. We introduced a new variable, which is zeta. And dual problem, we want to we introduce one new variable again, which is C. So we want to max. Let me write it as a dual problem. I'll write as a dual problem, which includes a quadratic programming algorithm, but is not. I have never gone into the, never used it till now. But again, for information, anyone can ask you what is dual problem. Dual problem is again a historical methods to you simply maximize. You introduce a CI where you want to maximize your function, which I'm going to give you a equation just over here. Okay, so here's the equation. So you want to maximize this f C1 all the way down to the Cn, okay, equals to I equals to 1 all the way down to the n. Ci, again a new variable, when Ci equals to 0, then the nearest data point is the largest. So you can see about the details on the internet about Ci, what are the things, what is the definition of a Ci, how it is used as a historical, but to just see how it is written, that it could quickly identify what is a dual problem, what is the primal problem. But if you're not understanding, don't worry, it's completely optional, this dual problem, okay, and that coordinate descent, completely optional. Okay, so you're just I equals to 1 j equals to 1 all the way down to the m. Now it's I equals to 1 all the way down to the m, then j equals to 1 all the way down to the n, yi ci times the dot product of ci, xi and xj, and then yi times the ci. I think so, I'm doing correct. Subject to I equals to 1 all the way down to the m, ci yi equals 0, and I'm writing and the ci should be smaller than or equals to 0, okay, and this ci should be in between 1 over 2 over n lambda, okay, and for all I. So this ci should satisfy this condition to be there. Okay, so this is the dual problem. You maximize this with respect to this. Okay, you can see ci times the yi. Okay, so great. So now this is the condition that you want to satisfy. And again, hyperplane are all the separate thing. They are all for prediction. We have already talked about prediction function. Now we are talking about a little bit of cost function, and now we are talking. Now we're gonna talk about a subgradient and coordinate system. So first we'll talk about subgradient. Subgradient is just like a gradient descent, but instead of taking a step at every data point, it takes a step at the vector selection, and this take a step into the vector selection. You can see how visualization over the internet, but what you are actually doing, you are just writing a convex function or differentiable function for minimizing the loss f of wb 1 over n I equals to 1 all the way down to the n, the max of 0 1 minus yi w transpose xi minus b, adding lambda term, which is lambda. Okay, and lambda determines obviously the width. Okay, so so this is it is just like a gradient descent, but it's taking out a subgradient, and you can search on internet what is subgradient. It's taking a subgradient of this cost function for minimizing, so so your loss function becomes obviously 0. Okay, so it's pretty much easy now. You may think, hey, primal problem and subgradient are mixture, and so, and they are easy. But there is also called coordinate descent, which is taking out the derivative here, which is taking out the derivative of your cost, which is the dual problem. You're taking out the CI with respect to adding the FI. Yeah. So you're taking out the derivative of your for your dual problem. For your dual problem. Okay, so it's just the same, and you don't have to worry about this. All things are implemented in Python. You don't have to just think about what is actually this and what's instead of we can do that. So what I recommend if you're doing what to choose, subgradient or maybe this dual problem, primal problem as an objective. So you can go with gradient, coordinate descent, and one more, which is what's the name? It's a subgradient. Okay, coordinate descent subgradient works best for larger training set, so you can go with that. Okay, and obviously another gradient of your cost function of hinge loss is obviously this subgradient. Okay, it works best with the larger, as introduced in the research papers. Okay, so now I think we have talked a lot and 43 minutes, and now I'm seeing 43 minutes are done in conversation. So now I'm going to talk about and spend some amount of time in 2 minutes on to empirical risk minimization. What is this? Empirical risk minimization means that you don't know how what algorithm will perform, because you don't know what's the distribution. You don't know actually how well the algorithm perform. That's called the risk, because you don't know anything, and that's called the obviously risk. So because you don't know what's the data distribution, so you can just put on the training set to train. So you want to minimize this empirical risk minimization. So you are given an x1 all the way down to the xn and its corresponding labels all the way down to the yn. So you want yn plus 1 to given xn plus 1. So you want the given input, you want output. Okay, so you can again the same thing I have to write. This you have to minimize. So we introduce an approach which is the loss of yn plus 1, which we want by model predicted, which is xx plus 1. Okay, this is the loss. Okay, and again the loss you can watch in cost function in my videos. Okay, and then for each and every training examples, 1 over n I goes to 1 all the way down to the m, l yi time or comma f x and plus 1. Okay, so this is for all training example, I think so. Okay, so this is the equation. Empirical risk minimization. You don't know how well our algorithm will perform because you don't know what the distribution of the data is. You always want to minimize this empirical risk minimization. So the last thing that I want to spend on talking about is support vector regression. What is support vector regression? SVR are kind of I will just give you the equation. It's just you want to minimize this 1 over 2, the norm of w square, subject to the absolute value of yi minus the product of yi xi, okay, parameter, and given some equation which is given some threshold. I think a greater is smaller than or equals to threshold, and this is just this is just a model prediction. Okay, so I think this is the equation that you need to get on, and support vector machine is used is everything you think so. And one more thing support vector machine is used, which is called the transductive. Obviously it's not too much. Transductive SVM. Transductive SVM can do in, it's called, if you know what semi-supervised learning, if you have some training example which is like a unsupervised training example, so it will transductive SVM would work, because we do provide some D when other set you can, but it's not necessary for now to study about transductive. When we go further in advanced, we'll talk about this transductive, but you know that transductive SVM can perform as to semi-supervised learning, okay, for an interview perspective, because they usually ask empirical risk minimization, they usually ask transductive SVM. Can you perform semi-supervised over there? Okay, can you perform if you have a less data? Yeah, you can perform that. Okay, so someone can ask you what's a dual, can you explain what is a dual problem? You can say, hey, your dual problem is like this. You introduce a new variable, and a problem we introduce one new variable zeta, and we simply want to minimize that with respect to that. Okay, and what is RBF, and can you explain that? Yeah, we can explain that, transform our data to be a linear data, and you can tell about a hard margin, soft margin, and linear SVM. You can talk about some examples if they want you to explain you about. You can explain that. You can revisit this video if you have an interview on the next day. Okay, so we have talked about everything you need to know about support vector machine, and I hope that you really enjoyed watching this video. And again, I think you have excelled in support vector machine. Each and every concept in support vector machine from every research paper have been taken. So all this PDF will be provided to you as in the form of PDF in the description down box below. If you want, I can give it to you. So thank you for watching this video. I'll be catching up in the next video. Till then, bye bye.